Hello, welcome to the control system lecture series. And this is the second lecture on the time response in list that will be basically on the first order system. So in the last lecture, we have seen that fundamentally there are four type of the signals that will be used. First one is a unit step signal, second one is a unit ramp signal, third one is a unit parabolic, and fourth one is a unit impulse signal. Because the signals are not fully known ahead of time, so it is necessary to study the standard test signal that will be used as a reference signal. So here in the first order control system, you can see that this is the transfer function, and that transfer function represents 1 upon st plus 1 for the unity feedback control system. So here the power of the denominator is highest power of the denominator is 1, means s ki power 1. So this will be called the first order control system. So since this is the plant, what we can say 1 upon st and unity feedback system. So transfer function of this will be cs by rs will be 1 upon st plus 1. So in the first case, we will use the unit as step input as a RS. Since RS is equal to unit step input, R means RT equal to 1. So Laplace transform of RT will be RS will be 1 by S. So in place of RS, we will put here 1 by S. So after putting in the transfer function, so Cs will become 1 upon S into St plus 1. So on partial fraction, this Cs can be represented as a 1 upon S minus T upon St plus 1. So this expression can further be written as 1 by S, and in the second term, if we divide it in numerator and denominator by t, so second term can be written as 1 upon s plus 1 by t. So on Laplace inversion, so this Cs can be written as a Ct equal to, since 1 upon S can be represented by 1 unit, and 1 upon S plus 1 by T can be represented as a 1 minus e ki power minus T by capital T. So here this Ct is a output, and since you know the error is between reference input and the output, means Et equal to RT minus Ct. So putting the value of Ct, here Ct is 1 minus e ki power minus T by capital T. So RT equal to 1. So 1 minus 1, this will be within bracket e ki power minus small t by capital T. So error is e ki power minus t by capital T, means exponentially decaying. So here in this graph, you can see that at t equal to 0, it has a highest value of error 1, while as the time passes, so this error decreases to 0 as t tends to infinity. While as the error decreases, so steady state value reaches to the unity value. So Ct will be reaching to the unity, since this curve represents the 1 minus e ki power minus t by t, since e ki power minus t by t decreases exponentially, so output will be reaching to the unity reference value. So the disparity between the output and input approaches to 0. So the steady state error in this case will be 0. So ESS will be limit t tends to infinity e to the power minus small t by capital T equal to 0. Now here in this uh, diagram you can see that output reaches to near the unity, and when it reaches to within the tolerance band of 2%, what we can say means that reaches to 0.98 value or 98% of the desired output. So that time is equal to 40, while at the uh, one time constant, each reaches to the 0.63 or 63% of the desired output. So this the time taken by the output to reach the 63%, it is called the one time constant or time constant of the system. So this is the basically time constant of the system, while it reaches to 98% in the 4 times of the time constants, and finally it will reach to the steady state value. So this when the signal reaches to 63% of the final output, the time is called the time constants, while after reaching to the 4 time of the time constant, the signal is the system is said to be is said that it has reached to the steady state condition. So before that it is in a transient state, and that represents that there is a still variation in the system that is reaching to the desired output. So you can see this is the effect of the time constants, and so you can see that the 4T is a demarcation between the transient part and steady state part of the time response. So when the actual output reaches within the 2% of desired value, so it is said to be the system has reached to the steady state condition. So 4T is termed as a settling time of the control system. So this 4T is said to be the settling time of the control system. Now the effect of the time constant you can see as we have a in this diagram you can see we have a two time constant, one is t1 another one is t2. So here t1 is assumed to be less than the t2. So in case of the uh, t1 time constants, so this will be reaching the desired output at a earlier than the time constant T2. So you can see if the value of the time constant is lower, so it will reach the steady state condition earlier, or otherwise if the time constant is higher, so it will uh, reach the steady state later. So that will take the more time, means settling time for the value of time constant which is greater will be higher, while the settling time for the lower time constant will be lower. Now case 2. So in this case the input is unit ramp input, means rt equal to t, means and the Laplace transform of this will be r, this will be rs equal to 1 by s square. Since the system is same, so cs will be equal to rs upon st plus 1. Since we are analyzing the first order control system, so the highest power of S will be 1. So now putting the value of Rs, Cs can be represented as 1 upon S square within bracket St plus 1. On partial fraction, you can obtain Cs equal to 1 minus St upon S square plus T square upon St plus 1, or further it can also be written as 1 upon S square minus T upon S plus T upon S plus 1 by T. On Laplace inversion, this can be expressed as a Ct equal to T 1 upon S square Laplace inverse is small t, while T upon S, since this is 1 upon S is a unit step, so on Laplace inverse this will be 1, so this will be capital T, while T upon S plus 1 upon T, its Laplace inversion is T into e to the power minus small t by capital T. So we have a output expression for the unit ramp input Ct equal to small t minus capital T plus capital T into e to the power minus t by capital T. So error in this case will be, as usual, difference between the reference input and the output, so that will be RT minus CT. Putting the value of RT and CT, RT equal to small t and CT equal to uh, T minus capital T plus T e to the power minus T by capital C. So on solving this, so we will get Et equal to capital T minus capital T multiplied by e to the power minus small t by capital T. So if for this steady state error, as t tends to infinity, ESS will be equal to limit t tends to 0 capital T minus capital T e to the power minus small t by capital T, putting the t tend to 0, since this term will become 0, so steady state error will be capital T. So there will be error between the output, between reference and the output, and that you can see here in this diagram. There are two curve. One is between output and time, another is between the reference input and time. So reference input is t, means RAM signal, so RT will be small t, so that is the this is the input, while output is, since it has a error, that is capital T equal to time constant, so this will be a curve like this, since it will be starting from this point and will rise like this. So there is a time lag between this, and also on a steady state there will be the difference between the input and this output of a capital T. So there is a time lag, not only a time lag but also a steady state error capital T. So here you can see how you can reduce the error. The error can be reduced if, once again, you can see the effect of time constant. If this capital T is smaller, so means time, so this is, since error is equal to time constant, so time lag will also be smaller. Not only the time lag will be smaller, but also the error at the steady state error will also be uh, less. So it is very important to see the time constant of the system. So if the time constant of the system is lower, so error at the steady state will be lower. Not only the error but also the time lag of the system. So here you can see the output velocity matches with the input velocity but lags behind the input by capital T. So this positional error of t unit exists in the system. So there is a error, steady state error, that is called positional error of the system. So as explained in the last slide, so you can see lower the time constant, lesser the positional error, lesser the time lag. Now the case number third, here the input is unit step, impulse input. So impulse input means as you can see that the Laplace transform of the impulse input is Rs equal to 1. So putting in the same system Rs equal to 1 means that Cs will be equal to 1 upon St plus 1. So you can see this is an on Laplace inversion. You can see that Ct equal to 1 by t e की power minus t by capital T. Since uh, for this case, the input will be at this. Otherwise, you have to take unit area input. So means it will be undefined other than the this axis. So we can not say about the error existence. So you have seen that for the first order system, first one is a unit step input, second one is a unit ramp input, and finally you have seen the unit impulse. So the major thing is that uh, time constant of the system. If the time constant is lower, settling time will be lower. If the time constant is lower, the time lag and positional error will be lower. So it is important to see that the effect of the time constant, and you can see the time constant. What is time constant? It is a when the time taken by system to reach the 63% of the desired output, while the settling time, it is a 4 time of the time constant. So this way, thank you very much. Please do like and subscribe this YouTube channel for